given by Ben Rossman about restriction-based method.
Okay, so let me start off by defining what I mean by restriction. So a restriction is just a subset R of the Hamming cube. And we'll be considering random restrictions, in other words, distributions of subsets of the Hamming cube. And the most common kind of restriction that I'll be talking about today are subcube restrictions. Okay, so and when R is a subcube, we can identify R with a function which maps the coordinates to either 0, 1, or star, meaning each coordinate is either fixed to a constant or left free. And RP will be the P random restriction, the most common random restriction we'll be looking at. So here P is some fixed parameter between 0 and 1. And here, so each variable is independently left free with probability P and otherwise set to 0 or 1 with equal probability. So restrictions are useful for proving lower bounds in circuit complexity. So a restriction can be applied to a function naturally. You just restrict the domain of the function. And certain kinds of restrictions can be applied to Boolean circuits and other objects syntactically. So to get a lower bound, well, if we can show that a circuit becomes simple under a restriction, while some target function remains complex, or perhaps with high probability, if R is a random restriction, then we get a lower bound. Okay, now there are different types of restrictions that one can consider and that they're used for proving lower bounds. Here, denoting them by the kind of constraints which correspond. So subcubes, you're just fixing coordinates to 0 or 1. More general kind of restriction would be a monotone projection where, in addition, you're identifying variables. You can think of this more traditionally as a projection by identifying all of the variables in a given equivalence class with a new variable. If we allow inequality constraints, we get projections where you can map to the negations of variables. Even more generally, one can consider affine restrictions where constraints are XORs of some variables are 0 or 1. And maybe the most general kind of restriction that I'll be talking about in this talk are restricting to a low degree variety, to the 0 set of some polynomials of low degree. Okay, so now that we all know what
strictly getting stronger as you went down?
Right, exactly. Yeah, or more general as you go down. So here's the outline for the talk. So I'll go through some background in circuit complexity and gate elimination arguments. I'll go through this fairly quickly. So next I'll talk about the switching lemma. So this will be sort of the main topic of the talk. And in particular, I want to show a new proof of the switching lemma via sort of entropy argument. And this actually leads to some stronger results, which I'll mention. Then I'll discuss some applications of these stronger switching lemmas. And I'll discuss a notion which I call criticality of Boolean functions. And we'll show how this new switching lemma gives improved bounds on the criticality of AC0 functions. And from this, we'll derive some other recent results, sharp-side algorithms for AC0, bounds on the Fourier spectrum, all follow from this result on criticality that I'll mention. And then finally, in whatever remaining time, I'll try to give a brief tour of some of the other random restrictions that are used to prove lower bounds, and maybe in particular focus on recent result of Hastad in proof complexity, so these site and grid projections. Okay, so that's the outline. Okay, so let's start with some background on circuit complexity. And I'll go fairly quickly through this since I assume everyone here is already familiar. So circuit complexity, we study the complexity of specific problems, such as parity or matrix multiplication, in combinatorial models of computation, and perhaps most importantly, Boolean circuits. And the goal is to prove unconditional lower bounds, so lower bounds which don't rely on any unproven assumptions. And I guess throughout this talk, whenever I say problem, I'm referring to a decision problem, but we'll regard problems as being represented by a sequence of Boolean functions, right, which are encoding the problem on instances of size n. Okay, so a Boolean circuit is a circuit comprised of, let's say, fan-into and/or gates and negation gates. We have our variables here on the bottom. By size of a circuit, I'll refer to the number of and or gates. So the negations are for free. So circuits compute functions. An n-variable Boolean circuit is computing an n-variable Boolean function. We say that a problem is solved by a sequence of circuits, one for each input size. If the nth circuit is computing the appropriate n-variable function. Okay, so this setting is in contrast to uniform models of computation, such as Turing machines, where we have a single algorithm that's solving a problem on all instances. So this is the setting of circuit complexity. Okay, so circuits given a very natural and important combinatorial complexity measure of functions. So the circuit size of a function is the minimum size of a circuit computing f. So the minimum number of and or gates you need to compute f. So from the early days of circuit complexity, we know that almost all n-variable Boolean functions have circuit size 2 to the n over n, both upper and lower bounds actually. And these are by, well, at least the lower bound is by a fairly straightforward counting argument. So it's important to emphasize the goal in circuit complexity is to prove lower bounds for explicit Boolean functions, specific functions in the class NP, say, such as cake-lick or parity, whatever. So the reason that circuit size is such an important complexity measure is that it's a sort of non-uniform version of sequential time. So if you have a Turing machine running in time t can be simulated by a sequence of circuits of size t times log t. So as a corollary, if one could prove a superpolynomial lower bound on the circuit size of any function in the class NP, then this would show that P is different from NP. In fact, you'd show something stronger, that NP is not NP/poly. And circuit complexity is widely believed to be the most viable approach to proving such separation.
ECT, come on.
What's that?
ECT.
Oh, all right, well. Okay, so the holy grail in circuit complexity, prove a superpolynomial lower bound on the circuit size of any problem in NP. Unfortunately, proving lower bounds on explicit functions is hard. So here's a table of some record lower bounds over time. We see there's been very slow improvement, and the best lower bounds we have today for Boolean functions is just shy of 5n. And right, if we allow parity gates as well, then we have something slightly better than 3n. So this is a recent result. And all of these results are proved using gate elimination arguments, which I'll discuss in a moment, using subcube restrictions in this setting and affine restrictions in this setting. Okay, so an important subclass of circuits are formulas, so De Morgan formulas, since I'm talking about the fan-in-2 setting. And formulas are just circuits with the structure of a tree. And we measure the size by the leaf size, so the number of leaves in a formula. And formulas intuitively are a weak model of computation in that they lack memory, in the sense that the result of each subcomputation is used only once. Okay, and despite this obvious weakness, it's open whether circuits are actually more powerful than formulas in the following sense. So, well, there can only be one holy grail, but you can call this maybe a pretty holy grail. You can hold paper clips. Prove that polynomial-sized circuits are strictly more powerful than polynomial-sized formulas. However, even proving formula-sized lower bounds is hard. So here we have sort of the world records over time. Currently, the best bounds we have are nearly cubic, with some recent log factor improvements of Avish et al. And here the main technique, well, it goes by the name of shrinkage of De Morgan formulas. So this is using the fact that De Morgan formulas simplify under p random restrictions. Okay. So, so we can't prove strong lower bounds for general circuits and formulas, so we study restricted classes in the hope of developing stronger techniques. So some of the main classes that we study are the AC0 setting. This corresponds to fast parallel computations, and these are Boolean circuits with unbounded fan and OR gates, but constant depth, or in general bounded depth. And the monotone setting, where we don't allow negations. There's also the arithmetic setting. You're computing over fields, and you have plus and times gates and tropical circuits and so on. And restrictions play a role in, well, at least in AC0 and arithmetic settings. So, so here's a generic picture of an AC0 circuit. So without loss of generality, we can put our negations on the bottom, and we have unbounded fan in and OR gates, so without loss of generality, nicely layered like this. And whenever I'm talking about AC0, the depth is always bounded by some constant d. Or if you prefer, d can be some slow growing function of n, up to around log n. One can, of course, also consider AC0 formulas, so AC0 circuits with the structure of a tree. And in this AC0 setting, very strong lower bounds are known. In particular, exponential lower bounds for each constant depth d are known since the 80s. So it's known that the depth d AC0 circuit size of the n variable parity function is 2 to the n to the 1 over d minus 1. Okay, and here again we have a technique using random restrictions. This is Hastad switching lemma, which we'll be looking at in some detail. And I want to point out that this kind of lower bound, this kind of dependence on d, maybe we could refer to this as a size depth trade-off. So the bound gets weaker as the depth increases. This is sort of a limitation of the lower bounds that are proved via switching lemmas. So note in particular that lower bounds of this form become completely trivial once d reaches log n. And this seems sort of inherent to techniques using switching lemmas. So I think to get stronger separations above AC0, random restrictions are not going to be enough. Okay, so some of the main lower bound techniques in at least the non-monotone setting, we have counting arguments, gate elimination arguments, these using restrictions, switching lemmas using restrictions, and the polynomial method, which I won't talk about in this talk. This is giving lower bounds against AC0 with parity gates. Just a brief word on this other restricted setting, monotone circuits. Well, so the point is we know essentially all separations among interesting monotone classes, and there are many, many different techniques. Restrictions aren't the main method used here. So a lot's known, and I'm not going to be saying much about the monotone setting. Okay, so on to an overview of gate elimination arguments and shrinkage of De Morgan formulas. Well, I should say, please feel free to interrupt me at any point with questions. Okay, so we're going to be talking for now about subcube restrictions. So we have a Boolean function f of n variables. So by restriction, we mean a function mapping the variables to 0, 1, or star, meaning unrestricted. Equivalently, you can think of r as a partial function from the variables to 0, 1. So we can, if we apply r to the function f, then we can view the restricted function as a function on the subcube over the free variables, over the stars of the restriction. Maybe here's a way to visualize that. So here's our restriction on the n variables. So we want the restricted function on 0, 1 to the stars. Well, you just combine these two and evaluate f. So, we can also apply a restriction R syntactically to circuits and to other objects. So what does this mean? Let's sort of illustrate this by example. So consider a 1-bit restriction. So the r here is, the only variable which it fixes is x2, fixes it to 1. So here we have our Boolean circuit. So when we apply this restriction, the x2 becomes the constant 1. So this 1 is feeding into these two gates, an OR gate and an AND gate. And so note that this gate is forced to the value 1 here, whereas this gate just loses this wire. So we have this simplification. And now this propagates, so this 1 now feeds into two different AND gates here, which kills these two wires. And then the final simplification step is, well, we can note that these three gates here all lost a wire, so we can bypass them and draw wires like that. So this is the effect of this 1-bit restriction on this circuit. Yeah.
You're mentioning this syntactic simplification, but I mean, all the lower bounds would work also under like crazy simplification that look on global things.
Yes, that's true. So for instance, right, when you talk about the shrinkage exponent, you're not talking about necessarily the action syntactically on the circuits, but on the leaf size. Yeah. Okay, so let's see, when I talk about gate elimination methods, here's maybe the simplest example of a non-trivial lower bound. So it's the following observation. If we have a circuit C, which is computing the n variable parity function for at least n being at least 2, then there exists a 1-bit restriction R, which kills at least 3 and and OR gates of the circuit. Okay.
Does that depend on the circuit computing parity?
Yeah, this is only, well, this is true of circuits which compute parity. It wouldn't be true of all circuits. Maybe I'll leave this as an exercise. Right. So, but in other words, if we apply the restriction R to C, then the size decreases by at least 3.
This is assuming your whole circuit is and or gates negation, right? It's not.
Yeah, right. By circuit here, I mean in the basis of and or not. Right.
And size is not including the NOT.
Yeah, size is not including the NOT gates here. And as a corollary of this lemma, so note that when you apply a 1-bit restriction to parity, you get back parity, either parity of n minus 1 bits or the negation of parity of n minus 1 bits. And this lemma would apply to 1 minus parity as well. So as a corollary of this lemma, we get a lower bound of 3n minus 3. And this turns out to be tight. Okay, so there's a matching upper bound. So I'll sort of leave this as an exercise. So this is, 5n is already state of the art, and here we've gotten at least something which is better than most trivial lower bound you can imagine, which would be just n.
This is for bounded or unbounded fan-in?
This is bounded fan-in. Yeah. Okay, so this is just to illustrate what is a gate elimination argument. So by much more sophisticated gate elimination arguments, we get the best state-of-the-art lower bound. So almost 5n for circuits in this basis. And then this recent breakthrough. So for a long time, 3n was a long-standing lower bound in the full binary basis. So all fan-in 2 gates. In particular, you have binary parity gates as well. And there was these guys came up with a nice argument giving I think 3 plus 1 over 86n lower bound. And here this is using affine restriction. So it's going beyond just subcube restrictions. Okay, just to mention some further applications of these 1-bit restrictions. If you're looking at depth D AC0 circuits, and you try to do, to greedily apply the best 1-bit restriction, deterministically, so you do this repeatedly, then the best lower bounds you can get, well, at least one lower bound you can get is of this form. So something barely superlinear, n to the 1 plus 1 over exponential in d. So this is the method of deterministic restrictions. You can get this for the approximate majority function. And a very nice algebraic version of this technique, which I wanted to mention from this paper. It gets essentially the same lower bound for AC0 circuits with parity gates via deterministic restrictions, which are actually low-degree varieties. So the zero set of some low-degree polynomials. So this goes by the name of the method of certifying polynomials. So it's interesting. It's maybe the only application of restrictions in the AC0 with parity gate setting. And I think a very interesting open direction is to come up with the notion of random restrictions in this sense.
Sorry, what exactly, what do you mean by low-degree variety? So you replace a variable with what, or you constrain the variables to?
You're looking at a subset of the Hamming cube, which is the zero set of some low-degree polynomials, and you say this is a certifying polynomial for your if your function's constant on that set.
You cannot think of this in a variable by variable manner.
Yeah, yeah, right.
Like the other ones. So this is it's a global.
That's right. Yeah.
What about TC0? Can it be applied also there?
So for TC, I mean, in general, we don't have. Yeah, I'm not too familiar with all the lower bounds in TC0 setting, so I'm not sure. But I think random restrictions also play a role. Okay, so right. So next, I'll talk about the most important random restriction that we'll be looking at is the p-random restriction. This is denoted RP. So this is, as I said before, independently for each variable, each coordinate, we're fixing it to, well, we're leaving it free with probability p and setting it to 0, 1 with equal odds otherwise. A convention throughout the talk, random objects will be written in boldface. So this very natural restriction turns out to simplify Boolean functions computed by De Morgan formulas, decision trees, AC0 circuits. So for these weak models of computation, these restrictions simplify these objects considerably. On the other hand, certain Boolean functions like parity maintain their complexity, remain complex under the p-random restriction, and this gives it lower bounds. So let's look at the effect of RP on De Morgan formulas, so Boolean formulas with fan 2. So I guess the first significant result in this setting of Subotovskaya shows that if f is an n-variable De Morgan formula, and you look at the expected leaf size of f under a uniform random 1-bit restriction, so pick a variable uniformly at random, set it to 0, 1 uniformly at random, then this decreases, is less than the leaf size of f. I think that should be, that does not look right.
Should be 1 over n. 1 over.
It should be 1 over n. 1 over n, is it?
1 minus 1 over n.
1 minus 1 over n. Yeah, 1 minus 1 over n to the 1.5.
Good.
But 1 bit, per 1 bit, it should be 1 minus 1.5 over n.
Ah, good. Right, okay, which is bounded by 1. Yeah. Good. Okay, so as a consequence of what should have been written here, the expected leaf size of f under a p-random restriction is bounded by order of, well, 1 plus p to the 1.5 times the leaf size. And there is a long sequence of works which were improving this exponent 1.5 all the way to 2, which is actually optimal. So this was a slightly weaker version of this bound was shown by Hustad. This in this form was proved by Avishai a few years ago. And so this 2 is known as the shrinkage exponent of De Morgan formulas. And this also, we get lower bounds also from this shrinkage phenomenon with formulas. So this quite directly implies a lower bound of n squared on the leaf size of the parity function. This is known by other arguments, like Kravchenko as well. But we also get the state-of-the-art, the strongest known lower bounds for a different function known as Andreev's function. These are nearly cubic lower bounds. So, right, this is the current frontier. So one open question which I wanted to advertise is, well, what is the effect of the p-random restriction on monotone formulas? So just like one has the shrinkage exponent for De Morgan formulas, one can define the shrinkage exponent for monotone formulas. And it's open what exactly this is. For the class of read-once formulas, this is known exactly what the shrinkage exponent is. It turns out to be something roughly, which is roughly 3.27. And it's conjectured that the shrinkage exponent of monotone formulas also equals this. This is an open problem. OK, good. So on to the switching lemma. Are any questions at this point? Yeah?
Is random restriction, is this technique used for at all against functions which are not closed under random restrictions or self-reducible?
Yes, I think generally.
It's hard to come up with a class of function that is not closed under restrictions.
No, I mean the Andre function is not closed under normal restrictions, and you still get lower bounds.
Yeah, that's good. That's a good example. Yeah. Right. OK, good. So, right. In order to state the switching lemma, let me first remind you what are decision trees. This is an even simpler model of computation than circuits. So we just have a tree where the non-leafs are labeled by variables. And, each non-leaf has a 0 child and a 1 child, and then the leaves are the output values. The depth of a decision tree is the maximum number of variables or queries on any branch. Right. So this gives a model of computing Boolean function. First, you read the variable x3, then you branch according to its value, and so on until you reach an output value. So the decision tree depth of a Boolean function is simply the minimum depth of a decision tree which computes that function. So for example, the decision tree depth of the parity function, as well as the decision tree depth of the n variable and function, is n. And having decision tree depth 0 is equivalent to being a constant function. OK, so the switching lemma speaks about depth 2 formulas, so also known as DNF and CNF formulas. So DNF for disjunctive normal form. So these are OR of AND formulas. So you have an OR of ANDs. Each of these ANDs takes literals, so variables are negations of variables. The width of a DNF or CNF formula is the maximum bottom fan-in, or in other words, the maximum number of variables in a clause. And so with K DNFs are simply called K DNFs for short. And note that a K DNF is the same thing as an unbounded fan-in OR of depth K decision trees. Okay, and similarly, CNFs are ANDs of depth K decision trees. So this follows from the fact that every depth K decision tree is equivalent to both a K DNF and a K CNF. I'll show this on the next slide. Just as an aside, there's a sort of weak converse here. So if a Boolean function is equivalent to both a K DNF and an L CNF, then it's equivalent to a decision tree of depth K times L. Just to illustrate this briefly, if you haven't seen it before, I mean, if I have a decision tree and I want to get a DNF out of it, well, simply for each one branch of the decision tree gives a clause, which is assignment to the variables on the branch, which lead to that output value. So here we get a DNF out of the decision tree. To get a CNF, you just do the dual thing on the 0 outputs. Okay, so here's the statement of Hastad's switching lemma, which is sort of the main tool for proving lower bounds against AC0 circuits. So if F is a KDNF, equivalently if F is an OR of depth K decision trees, then if we hit F with a P random restriction for any P, we look at the decision tree depth of the resulting function, then the probability that this is larger, is at least T, is bounded by some constant, 5 times pk to the T. Okay, this is the statement of the switching lemma. So this holds in general for any p and any integer t, but in general, one only really applies this when your p is something like 1 over 10k, so that this becomes like 1/2. So the way you should think about this is that, if we take p to be 1 over 10k, then we get an exponential tail bound. So the decision tree depth has an exponential tail bound. The probability it's bigger than t is at most 1/2 to the t. Okay, so there's also a dual version of this for CNFs. If you just replace CNF with DNF or with AND, then the same bound holds. And maybe just to mention the maybe more familiar version of the statement of the switching lemma is if f is a k-DNF, then the probability that f restricted on RP is not equivalent to a t CNF is bounded by this. This is a consequence of this. But we prefer to, this version will be more convenient to think about. So maybe just to illustrate, so here we have a k-DNF. We hit it with a random restriction where p is 1 over 10k. And then with probability, 1 minus 1/2 to the t, this becomes a width t CNF. So the way that this is used classically in a sort of depth reduction argument for AC0, we have an AC0 circuit with bottom fan-in k. We're going to hit this circuit with a random restriction r 1 over 10k, and we apply the switching limit to each of the second level gates, and we take a union bound over the failure events. Okay, and what we get is that these k CNFs switch to t DNFs almost surely, provided t is around log of the circuit size. Okay. Now, once you've applied the switching, you have two consecutive layers of OR gates. So you can combine them into a single layer of OR gates. And so you've reduced the depth by 1, and you've gone from bottom fan-in k to bottom fan-in t, or bottom fan-in log size. Okay. So this is the way that the switching lemma was used by Hastad. Okay, and so using this argument, you can show that the following lower bound for parity, which I mentioned before, that the depth d plus 1 AC0 circuits for parity have size which is exponential and n to the 1 over d. It'll be sort of just convenient from now on to index the depth by d plus 1. So before showing the lower bound, maybe it's nice to point out there's a very simple matching upper bound. So there exist circuits of depth d plus 1 in size, exponential in order n to the 1 over d computing parity. If you haven't seen it before, you can do this by induction. For depth 2 case, you simply have the brute force CNF DNF. And then for when d plus 1 is bigger than 3, you have sort of divide and conquer. So you take the brute force depth 2 circuit for parity over n to the 1 over d variables, and then you compose this with the depth d circuits for parity on n to the 1 minus 1 over d variables. And when you combine you can arrange this such that the gate types on the bottom here are the same as the gate types on the top here, so you can combine them to get depth d plus 1. Okay, and if you work out what size you get, it works out to this. Okay, so let me just illustrate briefly how, from the switching lemma, we get this lower bound for parity. So here we have a AC0 circuit. Depth is d plus 1. The size is s. So, at the bottom of the circuit we have variables or their negations, but let's just think of them as being depth 1 decision trees. Well, we want to apply the switching lemma. So each of these guys here is a 1 DNF. So we're going to apply the switching lemma with r 1 over 10. So it's just some constant restriction. And then what we get are a bunch of decision trees. And with high probability, the maximum depth will be order log s. Okay? So each of these individually has an exponential tail bound on its depth. And then if we just take a union bound, the maximum depth is order log s. Well now, okay, so assuming that this holds, then we're going to next apply a random restriction r 1 over 10 log s. And we're going to take the switching lemma with respect to these these CNFs, or these ANDs of decision trees. And again, we get the same picture. We get depth order log S decision trees with high probability. We repeat this, and then finally we repeat this up here. And what we get at the end, we have a decision tree whose depth is 0 with high probability. So what we're left with is a constant function with high probability. More precisely at the end of this process, we have a decision tree whose depth is almost surely 0 and then has some exponential tail down. Okay, so to summarize what we just did, we started with the AC0 circuit of depth d+1 and size s, and we applied a sequence of d+1 restrictions. First, there was a constant restriction, and then we applied p random restrictions where p was 1 over 10 log s. But you can think of the composition of these restrictions, well, as simply a restriction, an RP random restriction where p is 1 over order log s to the d. And what we showed is that this circuit under this restriction reduces to a constant almost surely. So this circuit under this restriction is almost surely constant. So on the other hand, the n-variable parity function under some RP, for any p, is almost surely non-constant when your p is much larger than 1 over n. To see why that is, note that what is the function we get here? Well, this will be either parity or the negation of the parity function on binomial NP many variables. So long as your p is significantly larger than 1 over n, this is almost surely not 0. So we have these two observations, and therefore it follows that the depth d+1 circuits for parity require size exponential in n to the 1 over d. You combine these two facts. Okay, so this is how random restrictions lead to lower values. Okay, so can we do anything better for AC0 formulas? So recall a formula. AC0 formula is just a AC0 circuit with the structure of a tree. So we saw this upper bound on the AC0 circuit size of parity. And if we simply take these circuits and convert them to formulas in the naive way, simply replacing whenever you have overlapping subcircuits, you replace them with disjoint subformulas. Do this repeatedly. Your circuits of size exponential in n to the 1 over d blow up to formulas of size exponential in d times n to the 1 over d. So we have this matching lower bound for circuits. So by applying the switching lemma in a more careful way to formulas, a few years ago I was able to show the similar matching lower bound for formulas. And this is a stronger result. This one implies this one, again by this naive simulation of circuits by formulas. So without going into any details, let me just explain the main idea and how do you apply the switching lemma in a more efficient way in the setting of formulas. So let's revisit this definition of the p random restriction, and let's sort of view it as a random process. So I'll think of this parameter p as representing some countdown time. So it will decrease from 1 to 0. And we're going to view the RP random restriction as a process as p goes from 1 to 0. So here's what this looks like. So to generate a random restriction, we're going to, for each variable, for each coordinate that is, we're going to take a random value in 0, 1 and a random timestamp, which is uniform random in the interval 0, 1. So here's what that looks like. These blue dots are the timestamps, and here's the random values. Now, at time 1, so at the start of time, then our random restriction will be all stars. So we only reveal the values of variables which are above this line here. So, okay, as p decreases, eventually we reveal the first variable, okay, and then another variable. At time p equals 1/2, roughly half the variables will be revealed, and so on. And eventually p equals 0, we've revealed all of our restrictions fixing every single bit. Okay. So just to illustrate in this dynamic view, what were we doing before when we applied Hostad's switching lemma to AC0 circuits? Well, we hit the bottom layer of our circuit with, we exposed it at time 1/10. And then we decreased this by a factor of 1 over 10 log s. And again, we revealed variables like this, and so on. Okay, so this is what we did. And we exposed each gate here at the time, which is simply determined by its depth in the circuit. And if you're talking about circuits, you can't really do anything more clever because you're already getting the optimal lower bounds. Okay, but what if we have a formula now? Is there something better we can do? And it turns out there is. So just to illustrate the idea, so what we're going to do is we're going to dynamically, for each subformula here, or equivalently for each gate in this formula, so call this one f, we're going to dynamically assign some stopping time, which I'll denote by q of f. Okay, so a different stopping time for each gate. Okay, so some q of f for this f. And so the way this is defined is sort of by a bottom-up induction. So to define q of f, okay, so assume we've defined the stopping times of each of its children. So we're going to let p be the minimum of the stopping times of the children of f. And then what we do is we're going to hit this, the subformula f with the RP restriction for this p. And what we get are some decision trees out of the switching lemma. And we'll let k be the maximum depth of these decision trees. So it's the maximum decision tree depth of one of the children at time p. And then this leads to the definition of the stopping time of f. It's going to be p over 10 times k. And I'm not going to say anything more about, I'm not going to say anything about the analysis of this stopping time and how it leads to better lower bounds. But intuitively, this is doing something useful. This adaptivity is sort of helping us.
But this is not a random read-once formula, right?
No.
How do you apply a random restriction with a different p for each subtree?
Yeah. So the key here is that so the underlying assignment to the values is the same, and we're just exposing them at different times. So you're right that it wouldn't make sense if we were taking different value assignments. Then that wouldn't make sense. So that's a very good question.
So the same input variable feeding into different gates is going to be exposed at different times?
Yes, but the value will be the same. Right. Okay. And the main technical result here is you prove a tail bound on this stopping time. Okay. So this is the theorem you get out of it. You get this extra factor of d in the exponent.
So can your thing be stated even for the two formulas? What's the simplest? What do you
yeah.
Are you able to visualize it for just step 2? What's going on?
Yeah, this doesn't give you so. You don't actually see an improvement. The constant here is actually worse than the constant here. So you need depth like 8 or something in order to get something better out of it. So just to point out, I've been talking here about the lower bounds for the parity function, but maybe more generally what these lower bound arguments give are upper bounds on a quantity known as the average sensitivity. Another way of, almost equivalent to this lower bound is the statement that depth d+1 circuits of size s have average sensitivity order log s to the d. And then for formulas, we get this extra factor d here, order d times log s to the d. Is that right? Or should
No,
it
it's
be 1 over d?
The other way
It should
around.
be 1 over d. Sorry, this should be log s over d. Yeah. And so what is average sensitivity? So the average sensitivity of a Boolean function is so you take a uniform random point in the hypercube, and then you're looking at the expected number of coordinates where the value of f changes if you flip that coordinate of x. So the expected number of coordinates I such that f of x is different from f of x flip I. So you flip the ith bit of x. Okay, so right, so now we come to sort of the main part of the talk, where hopefully I'll be showing something new to the experts, sort of a new proof of the switching lemma, which is based on a sort of entropy argument, and how this leads to stronger results. So I will show this after the break, but first I want to give a sort of as a warm up. I want to show you an even simpler argument, which is bounding the average sensitivity of size m DNFs. Okay, and if you get lost a bit when I give the proof of the switching lemma, then at least this is giving some of the intuition for what's going on. Okay, so let's consider now a DNF formula F, which is which contains m clauses. Okay, so it's C1 or up to Cm. Each clause Cl is going to be a conjunction of literals. So x1 and not x3 and x4, etc. So, I guess this I should have said here. So this should say if f has width k. So it's a very simple observation that if you have a k DNF, so if each of these literals has only k. So each of these clauses has only k literals, then there's a very simple argument giving an upper bound of 2k on the average sensitivity. And in fact, you can show that this upper bound is actually k. This was shown by Amano a few years ago. Okay, what I'm going to show is an upper bound of 2 times log m plus 1 using an entropy argument. I don't know whether this is a very simple. It's almost like a one-slide proof. I don't know if it's been observed before. Okay, and then I should say this isn't the strongest bound one can prove. You can, by reduction to the bounded width case, you can actually get something better here. But I want to illustrate this entropy argument. Okay, so here's what we do. So I'm going to consider a function associated with this DNF, which I'll call the first witness function, and I'll denote by f tilde. So f tilde of x is going to output the index of the first satisfied clause, if there is any. Okay, so the index of the first satisfied clause, if f of x is 1, and otherwise it will output m plus 1. Okay, and so the claim is that the average sensitivity of f is at most twice the entropy of the first witness of f. Okay, and because this random variable, the random variable f of x has a domain size m plus 1, then this is at most twice the log of m plus 1. Okay, so this entropy h of f tilde here, I mean the entropy of the random variable f on a uniform random point. Okay. And so this is basically a one-slide proof. So let's see. Okay, so here's just another way of writing average sensitivity. So average sensitivity of f is the sum over the coordinates of the probability that f of x is different from f of x flip I. Okay, probability over uniform random x. Now, if f is different on these two values, then the first witness function is also different. So we have this inequality. And now, so by symmetry, I mean, if these two values are different, one is less than the other. So this is equal to twice the probability that f of x is less than f of, that the first witness for x is less than the first witness for x flip I. Okay, and now we're just going to break up this event into these partition this event into the following events. We'll take the sum over all clause indices L of the probability that the first witness for x is the Lth clause, and the first witness for x flip I is bigger than L. And now all I'm doing is I'm exchanging these two summations, and I'm breaking up this probability into the probability that f of x equals L, and then the probability that f of x flip I, sorry, f tilde f x flip I is bigger than L, conditioned on f of x equals L. Now we can note that this probability here, this conditional probability, is going to be 0, okay, unless the else clause contains xi or not xi, okay? Because, so this conditioning means that this clause is 1. And for this to hold, this clause has to become 0 when you flip the ith coordinate, which means that the ith literal has to be occurring in this clause if this is non-zero. Okay, so now we can replace this by 1 if the else clause contains the ith variable and 0 otherwise. So we get the bound that this summation here is at most the number of variables in the else clause. Okay, and now we have this inequality here. I claim that the number of variables in the else clause is at most log of 1 over the probability that the first witness of x equals L. Maybe to see this more clearly, let's just rewrite this inequality in the following way. So the probability that the first witness on x equals L is at most the probability that the else clause on x equals 1, right? And, well, this happens with probability exactly 2 to the minus the number of variables in the else clause. Okay, and now we're basically done because this is the expression for entropy. Well, so here I'm just taking the sum of the first L values of the first witness. If you just extend this to m plus 1, then you have exactly the entropy of the first witness function. Yeah. Okay. So this is a very simple argument, which it doesn't depend at all on the width of clauses, right? It's in terms of log of the number of clauses, and
Is this tight? Is it
yes, this is basically tight.
the factor of, including the factor of 2?
Sorry, the factor 2. Yeah. So without the factor of 2, it should be tight. So by reduction to the width case, you can get like log m plus log m. Okay. Right. So there's some loss in this factor of 2. Right. So what I'm going to do is something actually quite similar to. So this is just something I noticed, and this actually prompted me to think about the proof of the switching lemma, and to try to do something similar. So. Right. 5 minutes before a break. I don't want to get deep into this, but I think I have. Maybe it's better, I think, to take a break now. Yeah, maybe we can start 5 minutes early again.
Is there any intuitive reason why we don't? I mean, this is a very formulaic way of arriving at the entropy function, right? I mean, you just have probability and some other log of the probability arising for completely. Was there have you tried to come up with a more?
Yeah. Actually, so this occurred to me when I was looking at this, actually a Mono's proof of the K over. So that's using it's using Jensen's equality together with the PPZ algorithm, satisfiability algorithm. Yeah, and that's where it came from. Yeah, I don't have a very good intuition for why the entropy shows up here. And in the proof I'll show of the switching lemma, it's not actually entropy that shows up, but a different function than we're using Jensen's inequality. Right. Any other questions? Yeah.
So one thing is that you can make it a bit tight is to get a better upper bound the entropy, right? Because like you sort of put like all the mass of like if it's I don't remember satisfiable or unsatisfiable, it's on the last one.
Sure.
So then like if it's balanced, you get like one element has like half the probability. And
yes.
And so then the log m plus 1 is like not tight.
Yeah.
Otherwise, you can probably get.
Good. So right. So I tried exactly what you're suggesting. So there's a different one. So right. So you get this bound right, 2 log m plus 1. If your function f has some expectation mu, you can get some other expression in terms of mu, something like mu times log m over mu, something like this. Yeah. Right, but of course it is interesting that we get an upper bound on average sensitivity in terms of entropy. So I don't know if the entropy of this first witness function is itself an interesting quantity that I'm not sure what you could do with it, but yeah. Okay, good. So after the break, we'll see the switching lemma.